The James Webb Space Telescope's first image was the deepest and most detailed infrared picture of the distant universe to date. It is called Webb's first deep field. A high-res image of the galaxy cluster SMAC 723 has an incredible level of detail. Thousands of galaxies, including the most distant and fainter one ever observed in space, were captured on film for the first time. The most remarkable thing about this image is that it covers a small part of the sky, the size of a grain of sand, from the ground up to where the person holding it is standing. While everyone couldn't help but be amazed by the pictures, sharp gravitational lensing, and webs of the deep field, something else important was hiding in plain sight that we nearly missed. Nowadays, it's possible to see individual star clusters and galaxies millions of light years away with the power of the internet. A notable case would be the one with the Sparkler galaxy near the center. They found not one, but in total 12 potential globular clusters surrounding it. But why are globular clusters called some of the most mysterious objects in the universe? So, what does this new discovery tell us about the time after the Big Bang occurred? There are two main types of star clusters, open and globular. The big difference between them is that open star clusters contain anywhere from hundreds to thousands of stars, while globular star clusters have tens or even hundreds of thousands. Open clusters are groupings of stars loosely bound by gravity. The number of stars in an open cluster varies, but some contain as few as 10, whilst other clusters may be home to up to 1,000,000 or more. They're usually unstable, and their constituent stars might disperse after just a few million years. That's why open clusters are mostly found in irregular and spiral galaxies, which currently have a high rate of star formation, and not within the elliptical galaxies, whose rate is lower. Concerning globular clusters, they are much bigger and more compact, so they will contain many stars tightly bound together by gravitational force. These clusters are commonly found in galaxies. In a spiral galaxy like ours, they are usually either in the halo or outer spheroidal parts. There are over 150 clusters in the Milky Way, and we don't know how they form. However, astronomers have been researching them since the 1970s, when they weren't well understood. The debate around how they were created still continues today, but there are two general views. Recent research has suggested that globular cluster formation is related to the assembly of galaxies in the early stages of the universe. This study proposes that the star clusters were created in the early universe, and their creation process is different from one driving present-day star formation. The second view of globular clusters is that they're the young stars seen in nearby star bursting and merging galaxies. So, according to this model, the formation of globular clusters is an inevitable outcome of continuous galaxy evolution. But since the absolute ages of most of the Milky Way is about 12.5 billion years, globular clusters are around that age too. The first thing that you think of when it comes to black holes is the way they seem to behave in relation to the early universe. However, recent research has shown that there are other astronomical bodies that formed earlier in our own history. This makes them a plausible candidate as one of the first large-scale objects that were formed in the universe. The new James Webb Space Telescope will help us distinguish observationally between these two galaxy cluster formation channels. That's because Webb can go as high in frequency as nanojansky flux and see far into the infrared spectrum. Globular cluster formation is best seen at higher redshifts. In their study, the researchers plotted data from a Webb telescope that had been trained to look for emission points around galaxies. They named this galaxy Sparkler. The galaxy we're in is from 9.1 billion light-years away. Sparkler has been gravitized by the various clusters of this constellation 723 in the foreground, and because of that, it has been magnified by a factor of between 10 to 100. The Sparkler galaxy has not only been magnified, but it was also difficult to see because of the gravitational lensing. However, the distortion and multiplication of its appearance also help further understand it. The sparkles can be seen in all three versions of the Sparkler galaxy, and these named points have only been found around the galaxy. But how do we know they are globular clusters? The answer is their stellar mass and density. Sparklers like this one typically have an average mass between 1 million and 10 million solar masses. This is consistent with it being a globular cluster that's about 13 billion years old. The Large Magellanic Cloud has a mass of about a billion solar masses. The Sparkler Galaxy itself has about the same mass. Out of these objects marked 1 through 12, number 9 hasn't been included in this report because the signal-to-noise ratio was too high. The objects marked 11 and 12 also extend into the host galaxy, nearly covering its entire area. Separating their light from the host galaxy is extremely difficult. Of the remaining 9 objects, scientists have confirmed that 5 are definitely globular clusters. This is the most important figure in the research paper. It plots the star birth rate of all of the 12 objects around a galaxy called Sparkler. Pink points and curves show the history of star formation that individual globular clusters went through. One of the remaining sources for oranges is from importers, from whom oranges are shipped to certain markets. The vertical axis is look-back time and horizontal axis is star formation rate. One can easily see a typical pattern. In the case of ancient globular clusters, every star-forming region had their peak in the early universe. The 9th object has a similar trend, but we can't make out its light because of contamination. It could be a globular cluster, but we're not sure. Astronomers first observed the trend of oxygen-3 in 500.7 N wavelengths. This spectral line only occurs in nebulas which are currently forming stars. However, it is absent from the globular clusters that exist on the outskirts of our galaxy, suggesting that these clusters are regular star systems and not close enough to Earth for their light to be subject to the interference. The researchers were interested in studying how globular clusters behave, and for this they analyzed the oxygen-3 spectral line maps. They found that these clusters are mostly quiet and therefore have a low luminosity state. This means they are finished forming their stars and are mainly constituted of old dying stars. This discovery is especially important because these globular clusters date back to over 13 billion years ago. They're one of the oldest clusters we've discovered to date. Furthermore, their color is consistent with stars originating in the first 500 million years of the Big Bang. This means they're around the same age as the universe's first galaxy. These particular ages were confirmed, after which it was found that the clusters are contemporary to large-scale reionization of the intergalactic medium. Which brings up a deep relation between globular cluster formation and the initial phases of galaxy assembly. One of the most important processes in astronomy is gravitational lensing. This process allows astrophysicists to better study the distant universe. This telescope will expose secrets of the cosmos that would otherwise remain hidden. For example, the discovery of Arundel, the furthest star observed in the universe to date, was made possible thanks to gravitational lensing. It is interesting to see what Webb will discover in these particular regions of space-time. Please like this video and make it go viral. Subscribe to our channel and press the bell icon so that you can make sure you don't miss any future episodes of this series.